This is Eric Collette again. Welcome back for those of you who have joined us earlier. It's my pleasure right now to introduce our next distinguished presenter, Mr. William Sims. William serves as the Director and Chief Engineer of Major Projects for Entergy Nuclear. In this role, he oversees all of Entergy's Peening projects. During his 32-year career with Entergy, Mr. Sims has had many first-of-a-kind designs and projects. I think that he could relate with Danny's talk earlier about pushing technology kind of over that hurdle and into production and implementation. Mr. Sims served as the chairman of the Electric Power Research Institute's Material Research Program, MRP Assessment Committee. While he was chairman, he led the development of MRP 335 to allow the use of water jet and laser peening to mitigate degradation of alloy 600 nuclear components, which is approved by the NRC during his tenure, and later NRC approved use of 2 ASME code cases for reactor vessel head penetrations and piping butt welds. Mr. Sims holds a Bachelor of Science degree in Mechanical Engineering from the University of Arkansas, and we're very pleased to have you here join us today and take your time to share your experience and expertise. So, William, I'll hand it over to you.
Okay, thanks, Eric. I appreciate that. At Arkansas Nuclear 1, A&O Unit 2, just this last outage in October. And this is a picture that you're looking at of the plant. On the left-hand side, this is our cooling tower. And on the right-hand side is A&O Unit 1 and A&O Unit 2. Unit 2 is actually the plant that we peened. And it's worth noting while we're on this slide that concrete structure, that's our containment building. And that's one of the reasons why we're having to peen, because we don't want to cut a hole in that containment building to replace that head. But I'll just go ahead and get started. So going on, get this picture out of the way. To define, the agenda is to define primary water stress corrosion cracking, give you a little historical perspective, and the long road that it took to get industry and regulatory approval for peening, and then talk a little bit about the peening that we did at A&O Unit 1 for bottom mounted nozzles, and then this that we just got finished with for Unit 2. But starting off, the primary water stress corrosion cracking. It's a cracking phenomenon that occurs in alloy 600 material that's at high temperature, tensile stresses, and the reactor coolant environment. The susceptibility is dependent on the material properties, the environment, the reactor coolant, and the temperature. The higher the temperature it is, the higher the probability of crack initiation. And same as tensile stresses, the higher the tensile stresses, the higher the probability as well. And then it's also time dependent. The longer time you have at these high temperatures and operating pressures and temperatures, the more probable that it is. On the right-hand side of the screen, you'll see a picture that actually shows a crack that occurred in A&O 2's CRDM nozzle. And you see this cracking that looks partly circumferential in direction. But this was discussed a couple of slides ago about stress corrosion cracking. You got 3 different elements, for primary water stress corrosion cracking: the tensile stress, the alloy 600 material, and the corrosion environment. In order to eliminate PWSCC, you got to remove one of these, and any one of them will work. If you take the different material, that'll work. If you get it out of the corrosive environment, high temperatures, that'll work. Or the choice for peening is to the tensile stresses. You convert the tensile stresses to compressive stresses, and then it will eliminate PWSCC. Of course, as you know, for a crack, if you're pulling it apart, it'll continue to tear. But if you're pushing it together, then it won't initiate, it won't continue to crack. This is just a figure that shows a typical combustion engineering plant. All of these labels that's shown on here has got different alloy 600 components, but a lot of these are small bore nozzles that you can't access to be able to go peen. But for A&O Unit 2, what we were looking at is the reactor vessel head. All of these in the red, orange color up here on top, the CRDM nozzles, the in-core instrument nozzles, and the one vent nozzle. That's what we were looking to peen for ANO2. For ANO, for a B&W unit, this is our ANO1 unit. And there's the CRDM nozzles up on top. And for them, you can also access the locations at the bottom. We call these the bottom mounted head instrument nozzles that we actually did peen. But again, there are several other Alloy 600 components, but the difficulty of getting to these to peen on the inside is, makes it essentially impossible to get to. Westinghouse is the other PWR unit or type that we have. Again, it has the CEDM nozzles up on top. And it also has bottom mounted instrument nozzles on bottom, but it also has main RCS loop, the similar metal welds, each one of these main pipes going into the reactor vessel. So that's the three different types of plants that we first started looking at, initiating or coming up with a mitigation process for PWSEC. Give you a little history that Bouget 3, a French plant, first found its first crack back in 1991. Because of that, our NRC regulatory folks, they decided that it would be a good idea that we need to be looking as well, and the industry thought the same thing. So we started trying to do some exams in the early 90s. In 1994, DC Cook was the first plant that found an ID flaw and ended up doing an embedded flaw repair. 6 years later, we were still struggling with this issue. Coney in 2000, Coney 1 found several instrument nozzles that had leaks, and then one CRDM nozzle. February the following year in 2001, Coney 1 had 9 CRDM nozzles. Well, our plant, ANO1, was coming up next in March. And it's worth noting, because of all these leaks, and these are on the highly radioactive head, and they were doing manual repairs of these nozzles, that they essentially dosed out about all of the welders in the United States, except for a handful. And so when it came our turn to do the repair, we didn't hardly have any welders left. And we had to do a unique repair, but that's a discussion for a different day. But also, Davis Vesey in 2002, as a B&W plant, they had not been doing inspection, nor is the industry good bare metal visuals. And they had boron that was left on top of their head for several years that from flange leakage from above that basically hid the leakage coming from below. And so they ended up having significant head degradation. And because of that, it raised the NRC's concerns that we need to be doing, volumetric and visual exams. So in 2003, they wrote an order mandating that all U.S. utilities perform these volumetric inspections. In 2008, rulemaking incorporated a code case N729, and that code case gave the requirements for volumetric and visual exams on these heads. Because of all this occurring, the high susceptible plants, we started replacing these reactor vessel heads where you could. And I talked to you earlier about the reactor building, the concrete structure, that if you had a big equipment hatch, then you could go ahead and install a reactor vessel head through that hatch. But if you didn't, then the preferred approach was whenever you replace the steam generators, then you replace the reactor vessel heads. ANO2, we were a little ahead of our time, so we had already replaced our generators in 2000 before this became a concern. So we were in a position that it would not be favorable to do a head replacement because we'd have to cut another hole in our reactor building. And later on, and I don't have a slide on it but Crystal River had tried to do a head replacement, steam generator replacement. They cut a hole inside their containment and actually had limestone as part of the aggregate in the concrete, and it actually caused some delamination. And because of that, that plant never started back up. So it's a pretty good safety concern, or it could be a concern, cutting that hole in your building if you have any crack like that, causing some issue. On the right-hand side, this actually shows you that figure, that picture that I had that showed the indication, the circumferential at the bottom, and then it goes axial up through here. But this, again, this was our early on crack back in 2001. So starting, back to mitigation, when all that started, Farley, they performed shot peening originally on alloy 600 generators back in 1987. And then in the mid 2000s, when we started having these nozzles failures, one of the repair methods was half nozzle repair. And in that, they used an abrasive water jet called AWJ and a later rotopeening process for the half nozzle replacement repair. That rotopeening and the abrasive water jet was used on the remaining alloy 600 component that was welded back in place. In 2004, MRP 118 evaluated different mitigation approaches, heat sink welding, mechanical stress improvement. And mechanical stress improvement was used on butt welds where they'd squeeze one end of the pipe and it would cause a compression stress on the ID surface. Corrosion resistant cladding overlay, that's used and still used today. Induction heat stress improvement, that's never did really take off. And then this emerging technologies, the emerging technologies was laser peening, low plasticity burnishing, and also water jet peening. So anyhow, this was the onset of us trying to develop some mitigation process for these reactor vessel heads. In 2006, MRP 162, and I guess I need to go back and say MRP stands for Material Reliability Program. This is part of EPRI, Electric Research Institute, that does research and technology. But anyhow, that's where most of this work was initiated from. But this document talks about the progress from 2005 and talked about the first nozzles that they wanted to try to mitigate. And in that, again, we was talking about cavitation peening, laser peening, and fiber lasing peening was the three emerging technologies. And I won't go into any details on these, but all of these reports that I have these links on, you'll be able to click on the link and look at the report if you'd like. In 2009, MRP 265 was initiated, and it was, again, determine the effects of different surface stress treatments. And again, you can go click on this, but you can see that water jet peening was included in that as well. In MRP 267, that is the primary technical document behind the justification that allows us to go peen. This document, was over the past two decades of stress corrosion cracking. It goes through that discussion, but then it talks about this document can be used for reference in writing relief requests. That if you met those requirements in the MRP 267, then you could ask relief. But of course, first we had to get that approved by the NRC. So in that effort, I was, as Eric mentioned earlier, I was the MRP assessment chairman, and we met with the NRC on June 9th, 2011. These are actual copies of our excerpts from that presentation. And again, you can click on the link and be able to view the entire presentation. But with that, we went over the NRC as the different locations that we want to go do peening, whether it be water jet, laser peening, or what we can refer to as fiber laser peening. And then I went over the different slides, for the industry, that it was our opinion that we could do this, in 2011 under the 5059 process and not even have to ask their permission. And in some cases, that peening was our only option to be able to mitigate without just extraordinary means. Like, for example, our Indian Point plant, the hot leg and cold legs, they were right next to the bioshield wall. And in order to be able to do a weld repair or weld overlay on that, you would have had to cut out that bioshield wall, and it's about a 3-foot thick wall. So you don't want to do that. So anyhow, I'm just highlighting the major points during that time period. We had the industry that they were interested in funding something to go develop that approach. And so we did know that we needed to develop the technical basis for it. And that once we did that and could get NRC approval, then we could go ask for a relief request. And the relief request would be not on being able to go peen, but for examinations. Like, for example, our reactor vessel heads, that code case that I mentioned, N729, for a hothead plant like A&Os that had an indication before, we're required to inspect that every 18 months. And that's about a $3 million hit every time we do that exam. So what these documents do is justify long-term inspection, or long-term intervals between inspections up to 2000 or 10 years on that exam. So with this, we concluded that we needed, further NRC engagement coming out of this meeting to go down that path of trying to get this approved. So the NRC in that meeting, they believed that no, that peening couldn't be done because it wasn't allowed by code, and that we would need NRC approval to go peen and to get any type of inspection relief. With that assessment group that I was chairman of, we initiated funding to go develop this topical report, MRP 335. But we did that primarily for the reactor vessel head penetration and the main RCS loop piping. The bottom mounted nozzles, we did not include into that document because the bottom mounted nozzles only required visual exams. We did want to go ahead and be able to peen them, but we wouldn't ask them for relief for inspections on that. This is another slide, back in the day, this was in 2013, that we did go through the effort with the ASME to prove that, to disprove the NRC's belief that we couldn't go ahead and peen. And there was 2 or 3 places that that peening was mentioned in the code. And so we asked for interpretations of that, justifying that we could go peen for our application, improving the stress of these alloy 600 locations. So the first MRP, first version of MRP 335, that was approved in 2012, but that was only improved by the committee and not by the NRC. 4 years later, we finally approved the Rev 3A version of that, and that was the approval by the NRC. The A gives you the designation that the NRC has approved that document. So it took us over 12 years. We talked about earlier how Danny was saying that somebody's pushing that. It's a long, hard road to do that. Well, this was that long, hard road. Took over 12 years, from once we started just on the heads. But, prior to that, we started having nozzle failures, back in the early 80s. So we've been working for over 30 years on these alloy 600 penetrations with these issues. But with this approval of MRP 335, now we could do peening and get NRC permission for inspection relief through that topical report. This is some sketches that shows our figures that shows the different head penetrations only. This is the ICI nozzle on the left-hand side. The blue or purple, that shows the inside diameter peening of the nozzle, and the red shows the OD peening. And the penetration in the middle, you can't tell it by the figure, but this is just a 3/4 inch nominal pipe size vent nozzle versus the one on the left-hand side, that inside diameter is a little over 5 inches. On the right-hand side, again, this is a CRDM penetrations, control rod drive nozzle penetrations, or control element drive penetrations. They're different depending on whether you're referring to a B&W, CE, or a Westinghouse unit. But again, it shows the areas that had to be peened to get that inspection relief. But what's important about this is the weld that's shown here, this in black, that's a little what the ASME code calls a J weld, or partial penetration weld. That's what causes the high residual stresses that initiates the PWSEC. Once that weld is installed with this very thick reactor vessel head. That head is over 6 inches in thickness. And once that weld cools and shrinks, it distorts this small bore or this nozzles from these CDMs and ICIs and vents. But that's what initiates that high residual stress. And by performing this peening, the peening puts that surface into compression stress, and then therefore eliminating PWSCC. So adopting MRP 335 now into ASME code. Once you get it into code, the NRC approves it, then you're no longer, sorry, I got things coming up on my screen. You're no longer required to ask NRC relief. So we started the ASME code case in parallel, after that 2011 meeting. And the first code case for the reactor vessel head 729-5 was the first revision, and -6 was the second revision. Those were approved by ASME code in 2015 and 2016. For the main RCS loop piping, that's code case N770-4 and N770-5 was approved in 2014 and 2017. Both of those were approved by the ASME code committee, but they were approved through the NRC through rulemaking in 2020. So, it took over a 16-year effort to, get this changed in the rules of ASME and by NRC to allow us to use these code cases. So now, once we, peen our hothead, plants like mine and do that second exam, now instead of every outage doing that inspection, I'm only required to do it every 10 years. This is just a picture of our inside of ANO Unit 1. This was our BMN nozzles, small diameter nozzles. We actually used fiber laser welding on it, and it was all underwater. And on this top left picture is just some of the equipment that was on top of the missile shields that was inside the reactor building. And then the right-hand figure shows where we put a tin over it and everything was air conditioned. And all these white cables, that's the cables to 4 different sets of equipment that was lowered down into this is our refuel canal over here on the right-hand side. And the tools were lowered down from this bridge into the reactor vessel to peen these nozzles. Going on to ANO2, we peened those with the LSPT's Percudo, the Percudo 200 laser peening system. Again, this tool, this laser system, this laser system was designed and it has a long durability of life. It has a high rep rate. It's a flexible process. You can change the energy, spot size. I don't know why it keeps moving on me, but pulse width and repetitive rate. And it has real-time diagnostics equipment. Now, when we were peening this outage, we did have one problem with the Percudo. We had an amplifier that did start degrading, and so we did stop the peening early. But this picture shows the Percudo here at the left. It shows the reactor vessel head here, and on top of the headstands. This figure shows the Percudo system. I don't know why, but for some reason my slides are auto forwarding for some reason, but it shows the articulating arm and the ROSA system that are where we move the end effector of the laser tool from nozzle to nozzle to be able to go peen. Again, this is the ROSA itself, the ROSA rail, and the articulating arm that the laser is piped into underneath the reactor vessel head. This shows a more detailed view of the end effector. And this one shows without a cover on it on the outside. But on the right-hand side, you can see this top port is where water is sprayed out onto the ID of the nozzle. This area here shows where the laser comes out. And then below here is where we have air that is jetted out that prevents debris. Air is blown from up above through past the laser and prevents debris from going back into the port and contaminating the mirrors. A little bit more detailed view. This is that 3D faceplate that all of the water and the air and the laser goes through. But if it wasn't for 3D printing, this process would not have been able to be developed. You can see on you can see on this figure that you can see this figure in the blue. Okay, somebody's moving my slides for me or something. On the blue is where the laser comes through. On the right-hand side is where the water comes through here, and in the third picture is the air knife. And this just shows a cross-sectional view of the space plate. This is the team that was put together. This was during our training process. It would consist of 67 people, 9 different organizations, as you can see there. You know, Entergy, Dominion, Westinghouse, LSPT, several others. But across that, we had project management, QA, optical, mechanical, electrical, controls, ROSA, and field services. Many of these people, especially those working from LSPT, had never been in a nuclear environment before, and that was a little treat for these guys, because you do have to dress out in anti-seize clothes to prevent from getting contamination on you. But the laser peening, the setup time, the load in, lay down time had 2 CLANs. Completed in 24 hours. All connections and startup equipment completed within the first 48 hours, and all the system checks and the tools, factory alignment, complete within 5 days. The system was waiting in standby for the NDE, the non-destructive exam, to be completed first. On the left-hand side, you can actually see the reactor vessel head and the equipment up above it. Attack in this in yellow here on the left-hand side, that's lead shielding around the reactor vessel head, and over here to the side is the Percudo system. This actually shows a picture underneath the head. This is the CEDM-ID tool. These right here is a ICI instrument nozzles. These are reactor vessel CRDM nozzles. This funnel helps guide the control element drive mechanisms into the nozzle itself. But this is our CEDM-ID laser tool that is inserted up into the penetration to perform the peening. Depending on the location, the outermost locations took the longest to peen. They took them just a little over an hour to peen, and the upper center locations, because this is on a hemispherical head, it was less area to peen, and it was about a 20-minute effort. But you can see that all the cables and airlines, and then this part here is part of the ROSA. Anyhow, well, on that peening, we did complete 42 of the penetration, 42 of the 81 in 15 days. We had consecutive runs of 12, 18, and 12. Like I said, our issues that we had was drifting of the mirrors. We originally started having a motorized mirrors that could be aligned through the computer, but we found that those were not rigid enough and weren't accurate enough. So we stopped doing that with the motorized mirrors, but we left the motorized mirrors in place. But what we found during the operation is that these mirrors actually moved and drifted some. And so after 12 to 18 penetration, we'd have to go back and realign the Percudo. But like I said earlier, we did have one tooling issue with the Percudo that that we did have an amplifier that was degrading, and we ended up stopping the peening before we completed all 81 penetrations. But that's all I have. You know, any questions, I'll open it up.
Thank you very much, William. I guess looking to my folks here in the room, any questions come across the chat for William? Okay, we do have one question.
David Larman, William, I got a question. Certainly you've been leading the industry, the nuclear power industry, with implementing laser peening into this type of an application. I'm just curious, from your perspective, at what point did you feel or say this is the technology to proceed? What event or what piece of information kind of convinced you of that?
I was down that path back in around 2012. Because when we were doing that review, that these penetrations that I show you here with these funnels, we had three different options. We had the fiber laser peening, and we had laser peening, and then we have water jet peening. The water jet peening, and this picture doesn't do it justice, but these funnels, if you look at a plan view of them, there's only about a 2-inch clearance between the funnels. And with water jet peening, that requires you to remove all of those funnels to be able to do the water jet peening itself. And these nozzles that, this is that little J weld that I'm showing you here, is the part that we're peening, and then a couple of inches down below. But if I cut these funnels off, then that causes me to have to re-weld those funnels on, and that causes another initiation site, which I really don't want. But down at that area, even if it did initiate a crack, it wouldn't be a through wall leak. But again, it would cause me to have to cut off all the funnels and re-weld the funnels back in place, and that's a significant amount of time. What laser peening does for us is that, since it has the capability, at least with LSPT's laser tool, that you can, shoot a distance, beyond 2 feet away from it, it allows me to have the laser and all the tool where I don't have to remove that funnel, and I can get into what's hard also to see is this lower hillside. Is this curvature. It's a nice steep hillside to be able to get a laser up in there. So with a laser, if you can see it, you can peen it. But if I, with the laser shock process that LSPT has, but if I was trying to do a fiber laser that's only that only has a millimeter, 2 millimeters distance that it shoots, then you actually got to mechanically move a mechanical part to point the laser up in that area. So, that led us to something, like LSPT has with that capability to shoot several feet away, where, as long as you could, shine a light on it, then you ought to be able to get the coverage.
Great.
Thank you.
Thank you, William.
Yeah, thank you, William. And we have another question that came across. Danny, I'm glad that you're back. I assume that you could probably relate to a lot of what William's talked about. So Danny's question is, after 16 years of approvals, what is left to transition? And William, do you see any technical hurdles ahead?
I don't see any technical hurdles other than, it's going to be different for different plants. For us, for our CE unit, we have the smallest diameter head in the industry, and then we also have the shortest nozzles. So for us, okay, we have this tool that's designed that we can go peen. But if you're trying to use the same technology on a Westinghouse plant, for example, and I didn't, give you pictures a bit, the Westinghouse plants have thermal sleeves up inside their nozzles. So one of the issues is trying to peen behind the thermal sleeve. The competing vendor with water jet, he's able to stick his nozzle up in between the thermal sleeve and the nozzle, but he's only able to peen and get a quarter millimeter depth compression. Well, peening, you want the more compression, the better. But for laser peening, the process that we was going to use with our Indian Point plants, Westinghouse plants, was we was going to put an EDM slot on that thermal sleeve, and then we was going to pass the beam through the slot and to be able to peen the ID of the tube and still get, 1 millimeter depth compression, which is, 4 times what water jet peening can do. So that's a different tool design, but once you got the bases down, like we have with this first set of tools, it's just a modification of the tools to be able to get it to do a different plan.
All right, thank you, William. We have another question that's come across. Any perspective on ROI of the implementation?
I'm sorry, what was that again?
The question is there any perspective on the ROI of laser peening in the nuclear industry?
I'm not sure what you're meaning on ROI.
Return on investment.
Well, the for for Entergy, like I said, our plant, if we had to replace the reactor vessel head and cut a hole in containment, it would have cost more than double or triple what it would to do laser peening. I say double now. When we first started, we thought it was going to be a factor of 5 or so, but it's taken us a lot longer to get this process approved than what we originally anticipated. Of course, we we went through and started working with Westinghouse and Toshiba, and then of course that had a bankruptcy issue, and then swapped vendors to LSPT, and probably for the better anyway, because they had the fiber laser that wasn't going to be able to get in on the downhill side. But I expect for the other utilities that come in, second and third, it'll probably be a factor of at least 2 or 3 savings as opposed to a head replacement.
Okay, thank you for that. Just taking a moment here and seeing if anything else comes across.
It's possible to peen painted metal.
I guess a question from Sergey: is it possible to peen the painted metal? It could be interesting.
We haven't tested for painting or for peening painted metal, I guess. Well, I'd say that I may be in error, because some of the heads do have some paint on the inside of them still remaining, but all of these heads, if you looking at this picture that I've got on the screen, that's a gray oxidation layer, gray blackish color. So it's got a fairly thick film of oxidation on it that we're able to peen through that into the metal. So I wouldn't see a problem with being able to peen over paint. So some of these reactor vessel head do have some painting on that's left, remnants that's left on the ID.
Thank you, William, and thank you, Sergey, for the question. I think David Larman has a bit of perspective just from our experience with peening on painted materials.
Yeah, so one of the things we used to use as an opaque overlay was a particular type of paint that we actually use as our opaque overlay to laser peen parts with. In more recent times, obviously, we have gotten away from using that, but it is possible to laser peen with paints. But you got to be very cognizant of the species that are in the paint, because those are important in terms of generating the plasma and the subsequent shock wave that cold works the material.
Okay, thank you, David. Thank you very much, William. I think we're ready to spin this one down. So appreciate everybody that's attended and asked questions. William, thank you again very much for taking part in today. We have a question that's come in late. Unfortunately, I think we're gonna spin this one down. So we'll try to get back to you on that one. We'll be rejoining here in approximately 20 minutes when we'll be introducing Dr. Stan Bobid. So thank you, everyone. Thank you, William.